Today we're going to be talking about dilations. So we've talked about translations, we've talked about reflections, rotations, and now we're talking about dilations. And when you think back to what you did in Algebra 1, dilations are like your vertical stretching or shrinking. So a dilation is a transformation that stretches or shrinks a figure to create a similar figure. I'm going to highlight a couple key words here. One is dilation, vocab word. Another one is similar. The reason similar I'm highlighting is because that is a vocab term for geometry. It's similar to what we think of when we think of similar in our everyday language. So when we use the word similar in our everyday language, like this homework assignment is similar to last night's homework assignment. Similar means that they're alike, but they're not exactly the same. So it's close to being the same, but it's not the exact same thing. So that's what we use in our everyday language. And if we think about it that way, it's going to help us understand what similar means in geometry. But in geometry, it has a very specific meaning. So when we perform a dilation today, we're going to talk about the qualities of a dilation. And it's going to help us come up with what similar means in geometry. So in order to dilate something, we need a figure to dilate. So let's talk about a triangle. So we'll do triangle, we'll call that JMV. And when you dilate a triangle, the first thing you need to know is what point are you going to dilate from. So there's always a point that you're going to dilate from. So let's make that point right here. We'll call this point N. And when you dilate from a point, what you're doing is we'll go ahead and draw in this ray J or NJ. We're saying that we are going to take this distance and we're going to either double it, triple it, cut in half, do something to figure out where J prime is. So that's how we're going to stretch or shrink. Now, this distance right now, if I take my ruler, we'll use centimeters, is, what does it look like? About 1.1 centimeter, no, 1.6. We'll say it's about 1.6 centimeters. So this distance right here is 1.6 centimeters. I'm going to stretch this or enlarge this by a scale factor of 2, which means instead of having the distance be 1.6, it's now going to become 3.2. So this here is where J prime is going to go. So here we have J prime. So we just dilated J by a scale factor of 2 from N. So this distance is now doubled. We can do the same thing for the other points as well. So if I draw in ray NM and ray NV, this distance right here was originally 1.4. It's now going to become 2.8. And we'll say this now is where M prime is. And this distance right here, if we measure this, was originally exactly 1 centimeter. Now it's going to be 2 centimeters away. So point V prime is now 2 centimeters from N. And if we connect these points, we will have the triangle J prime, M prime, V prime. So this triangle has now been dilated from a point N by a scale factor of 2 because this distance from the center of dilation to any point is now doubled to get its image. So when we look at this, we're thinking, well, is this an isometry? Well, if we go ahead and I'm going to trace JMV. This isn't cut. Let's see if this works. Alright, so we got JMV. If I try and use this tracing paper, I can clearly see, and I probably could have seen it without using tracing paper, that this guy is not the same side. So side length is clearly not preserved. And if it's not preserved, what does that mean? Well, it means that this dilation is not an isometry. But something is preserved. If I scooch this over, this was triangle JMV. I line up these angles, I'll notice that angle J and angle J prime are congruent. That angle measure was preserved. And if I go back here, this is angle V, I slide it over here. Angle V and V prime are also congruent. I can do the same thing for angle M, and I see that these angles are also congruent. So side length is not preserved, however, angle measure is. So go ahead and mark in this picture where we have congruent angles. When you look at it, angle V will be congruent to angle V prime. Angle M and M prime will be congruent, and angle J prime and J will also be congruent. So to conclude, a dilation is not an isometry because side length is not preserved. However, angle measure is. So what we can say about these two triangles is that angle J is congruent to angle J prime, angle M is congruent to angle M prime, and angle V is congruent to angle V prime. So angle measure is preserved, or these corresponding angles are congruent. So I want to take a further look at these side lengths then. We created this dilation by taking Jn and doubling it, which means that the ratio of J prime n to Jn, so this length to this length, will be equal to 2 to 1. This will be double whatever this is, or just 2. And it's the same thing here. We have V prime n, this distance, compared to Vn, will also be equal to 2, which will also be equal to M prime n over Mn. The ratio of this distance from the image to the center of dilation to the compared to the pre-image to the center of dilation will give you this too. It will give you what the scale factor is. So when we look at this ratio, please take a note that on the top is your image, or the ending, and on the bottom is your pre-image. And when you take this ratio of these distances, it will give you the scale factor. So that is your scale factor right there. We could also measure these side lengths here. And if I measured this guy compared to this guy, that guy compared to that guy, and this guy compared to that guy, I would see that those ratios are also the same. They're still equal to 2. So I'm going to write this down here. We can see that J prime M prime over Jm will be equal to M prime V prime over MV, which will be equal to J prime V prime over JV. So I specify the difference. This is talking about the distance from a point to the center of dilation. This is just talking about the side lengths of the triangle. These ratios will still be equal to 2, so it's still the scale factor. But now when we talk about the side lengths, if the ratio of the side lengths are equal, then we can say that the sides are proportional. So this means that the side lengths are proportional. Side lengths are proportional. So the angle measures are preserved, the angles are congruent, and the side lengths are proportional. This right here is the definition of similar figures, or in this case, similar triangles. We're not going to talk a lot about similar triangles right now, but we are going to dig into that in Unit 6, second semester. So I just wanted to show you when we dilate, this is what we get. We get that triangle JMV will be similar to, so it's this little wavy thing. It looks like kind of the top of a congruent symbol, but it's not congruent. That means triangle JMV is similar to triangle J prime, M prime, V prime. This notation right here and the side lengths being proportional is not super important right now, but it will come into play later on this year, so I thought it was worth mentioning. All right, so the last thing I want to talk about here, just about dilations, is when we name a dilation, we have to talk about what we need. Well, the first thing is you got to tell me it's a dilation. Okay, but if I just tell you to dilate something, you'll have no idea where to start. So think through, well, what else did we need to know before we started dilating? Well, we needed to know what point we are dilating from. So if I were to describe this dilation, this would be a dilation from point N. And in order to figure out where the prime was, I had to figure out, well, what was that distance? What scale factor was I doing? So it was dilation from point N by a scale factor of 2. Now, this was a scale factor of 2, but I could have done a scale factor of 3, and instead of, if this was 1 centimeter, instead of going 2 centimeters, I would have gone 3 centimeters. Or I could have done a scale factor of 2.5, so I would have gone 2.5 centimeters. There's all these different dilations, or different scale factors we could use. Okay? So I want to use what we just talked about then, excuse me, to do number 1. So I want you to pause this video and think through this on your own. If I have a scale factor of 3, and I want to go from the origin, I have this triangle, here's the origin, try and figure out where is B prime going to be. If this is where B is, where would B prime be? Now we have a coordinate plane. You don't need a ruler to do this. You guys can figure this out just by counting with the coordinate plane. So in your groups, or with the person sitting next to you, try and figure out where would B prime be. Pause the video and do this right now. All right, so now that you've tried this on your own, I'm going to talk through it with you. I know that B prime is going to be on the ray from the center of dilation through B. So I'm going to draw this ray. I rise 5, run 1, rise 5, run 1, rise 1, 2, 3, 4, 5, run 1. So B prime is somewhere on this ray, and I'm going to draw it lightly just so we can kind of see where it is. B prime, though I know if it's a scale factor of 3, will be 3 times the distance from the origin as B is. Well, because we're on a slant, it's hard for me just to count, so I'm just going to do the rise in 1. I rise 5, run 1. So that distance, that's one of the distances. I want B prime to be 3 times that away. So I can do that 1, 2, 3 times from the center of dilation, and this right here will give me B prime. So this guy is B prime. Now there's another way we could have done this. We could have said, well, if I rise 5, run 1, to get to B prime, I have to do triple that. I'd have to rise 15 and run 3, and you jump to it right away. That's another way you could have done it. So if we do it for the rest of these, here I rise 3, run 2, rise 3, run 2, rise 3, run 2. So I know that A prime is going to be somewhere on this ray, and I need to triple the distance from the center of dilation to A. So here's one distance, rise 3, run 2. I need to do that 3 times total from the center of dilation, or 2 more times past A. So 1, 2, 3 times that distance, and there is my point A prime. So I can label that A prime. Excuse me. And for C, I rise 4, run 5, rise 4, run 5, rise 1, 2, 3, 4, run 1, 2, 3, 4, 5, and so on. And when I do that, again, I know that C prime is somewhere on this ray, but the distance from the center of dilation to C has to be triple now. Or sorry, the distance from the origin to C, I will triple that to get the distance from O to C prime. So the origin to C, there's 1, 2, 3 times, there is C prime. So now I can draw in this triangle. And there is the triangle that's been dilated from the origin by a scale factor of 3. Naming the congruent angles, I realize that B and B prime correspond, so angle B will be congruent to angle B prime, angle A will be congruent to angle A prime, and angle C will be congruent to angle C prime. Now, the next one, though, wants me to dilate by a scale factor of 2, so not 3 anymore, just a scale factor of 2 from point A. Go ahead and try and reason through this one on your own before watching how I do it. So pause the video and try and do this on your own. All right, now that you've tried this on your own, let's talk through this. This center of dilation is point A now. So here's point A. So I'd still do the same reasoning. So now C, I rise 1, run 3 to get to C, which means I'll have to rise 1, run 3 twice from the center of dilation to get to C prime. For B, I rise 2, go to the left 1, which means I have to do that twice from the center of dilation, rise 2, left 1 twice to get to B prime. Now A, I think through, well, how far is A from the center of dilation? It's 0. So if I double 0, I still get 0. A prime lands right here. So the triangle is this guy right here. And there is number 2. Now that we've talked through number 1 and 2, go ahead and do number 3 and 4 on your own. So pause the video, try these on your own right now, work with people around you, and then let's see how we do. Alright, so I'm going to talk through these now. Dilating DEC by a scale factor of 1/2 from the origin, so the origin is right here. So if I dilate by a scale factor of 1/2, well, let's go from D. Here is this whole thing. So to go to D, I rise 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. I rise 15 and I run 3. Well, instead of rising 15 and running 3, I got to go half that distance from here. So I'm going to rise 7.5. 1, 2, 3, 4, 5, 6, 7.5. And I'm going to run 1.5 right here. And this is where D prime is. I'll do the same thing for the rest of these. To go from the center of dilation to E, I go up 1, 2, 3, 4, 5, 6, 7, 8. I go right 1, 2, 3, 4, 5, 6. So up 8, right 6. Now I want to go half of that. So I'm going to go up 4, right 3. And here is E prime. And if I do the same thing through C, I go up 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So I go up 10, right 2, 4, 6, 8, 10, 12, 14, 16. So up 10, right 16. I'm now going to go up half of that, 5, and right half of that, 1, 2, 3, 4, 5, 6, 7, 8. And there is C prime. So now I have a dilation of 1/2. All right, and I can do the same thing, but now from point C. So if I dilate by a scale factor of 1/2 from point C, here's point C. To go from point C to point E, I go down 2 and left 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So I'll go down 1 and left 5, and there's my E prime. And maybe I should be using double prime to denote it's different, but double prime typically means a second transformation, and we're not transforming from this guy. So I guess I'll still use E prime. Don't let that confuse you. So to go from C to D, I go up 1, 2, 3, 4, 5. So now I'm only going to go up 2.5. I go left 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So now I'm only going to go left 6.5. Yeah, 6.5. 6.5. Okay, so I'm going to go up 2.5, left 6.5, and there is D prime. So now I have my final triangle here. Okay? When you look at these dilations, one of these represents, or one graph represents enlargements and one represents reductions. And I think we can see that here, if we started with a small triangle and it got bigger, this right here would be an enlargement. So these guys are enlargements. And these guys over here are reductions. Enlargement meaning we're going to get bigger. Reduction meaning we're getting smaller. So what I'd like you guys to try and do is think through, what do you think that the scale factor would have to be in order to make an enlargement? And what would have to be to make a reduction? So I'm going to say K is the scale factor. For an enlargement, what does K have to be? And for a reduction, go ahead and pause the video and try and think through this on your own. Now that you've thought through it on your own, here for it to be an enlargement, notice here both of these, the scale factor is bigger than 1, and in order to make that distance or this shape bigger, we'd have to go further than the 1 unit from the center of dilation to a point. So if K is greater than 1, we will have an enlargement. In other words, if the scale factor is greater than 1, it's an enlargement. For a reduction, This will be if it's less than 1. We're shortening that distance. We have to specify, though, it's also greater than 0. You're going to explore later on what it looks like to have a scale factor that's negative. Right now, I just want to focus on the fact that between 0 and 1 will give you a reduction. So then what if it's equal to 1? What will happen? Well, if it's equal to 1, that distance will stay the same, so you'll have the same figure. The figure does not change. So if it's equal to 1, that figure will not change. All right? So the last thing we're going to do today is come up with a coordinate rule. So it says a function rule in coordinate notation, meaning your x, y goes to something for a dilation. So I want to specify this is a dilation. Specifically, at the center is 0, 0. So we have to specify the center of dilation. That's 0, 0 by a scale factor of k. So these three things. So you have a scale factor, you have a center of dilation for both 1 and 3. So that's my blue and my orange one. And I want you to think through, how could you write a coordinate rule for that? Pause the video and try and think through, what would the coordinate rule be if the scale factor is k, meaning it could be any constant. All right, so now that you've hopefully thought through that on your own, if we look at these coordinates, what we can see is that A was originally 3, 2. B now, what is that? Yeah. No, sorry. 2, 3. Oops. 2, 3. A prime would then be, if I dilate by scale factor of 3, we saw that this ended up being 6. 1, 2, 3, 4. 6, 9. Or B used to be 1, 1, 2, 3, 4, 5. And B prime is now 3, 15. Similarly, if we look over here, E used to be 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, 7, 8. And now E prime is 3, 4. So what we can see is these are now half of that. Or if I multiplied by a half from the original, I would get the image. If I multiply these coordinates by 3, the scale factor, I get the image. So here, as long as the center of dilation is at the origin, I could take that scale factor and I multiply by those coordinates and I get my image. Again, that's only if the center of dilation is the center. So that is our summary of dilations.